Welcome to this explainer. Today, we're diving straight into the microscopic world of atomic impurities. We're going to explore exactly how N-type and P-type semiconductors are created, and more importantly, how they come together to create the electronic device functionality that powers, well, literally everything around us.
Think about it for a second. It's a pretty fascinating question, right? How does a microscopic, practically invisible slice of rock end up powering your smartphone, your computer, and the entire internet? The answer starts all the way down at the atomic level, where trace amounts of invisible elements completely transform standard silicon into an absolute technological powerhouse. Okay, here's our roadmap for this explainer. We'll hit the silicon conductivity problem, break down semiconductor doping, compare N-type and P-type materials, look at the mighty PN junction, and wrap up with how all this powers modern electronic devices. Let's get right into it. Section 1. The silicon conductivity problem. Our story begins by looking at incredibly pure silicon, which, in its natural state, actually presents a massive roadblock for engineers. Look, pure silicon has this beautifully structured crystal lattice, but here's the catch. Undoped silicon is a terrible conductor. In its intrinsic state, all of its valence electrons are perfectly locked up in covalent bonds with neighboring atoms. Because there are no free charge carriers, literally no electrons roaming around, it acts way more like an insulator. So if we want to build a device that processes electrical signals, pure silicon alone just isn't going to cut it. Moving on to Section 2, Semiconductor Doping Explained. To fix this giant fundamental roadblock, scientists bring in a little magic ingredient, a process that completely flips the material's electrical behavior on its head. And by magic ingredient, I mean a process called doping. We're talking about taking that perfectly pure silicon lattice and intentionally introducing foreign atoms. But this isn't just haphazardly throwing stuff in. It is done in minuscule, highly controlled quantities to engineer the exact electrical properties we need. As the folks over at WaferPro point out, these impurities modify the silicon's natural conductivity in incredibly valuable ways. By adding these precise trace elements, we actually gain the flexibility to transition materials between conductive and resistive states based on operating temperature or applied voltage. This flexibility is the very essence of a semiconductor. It doesn't just always conduct or always insulate. It gives us the power to flip the switch and control the flow of electricity. Which brings us to Section 3, N-type vs P-type. This is where our two main characters enter the stage and the semiconductor story really gets going. If you look at the periodic table, there's this perfect, almost poetic symmetry between these two types. N-types use group 5 elements to act as donors, providing us with extra negative electrons. P-types, on the other hand, use group 3 elements to act as acceptors, creating positive charge carriers that we simply call holes. Honestly, the easiest way to think about it is like a microscopic game of musical chairs. N-type materials bring extra players to the game with their donated electrons, which are totally free to move into the conduction band. P-type materials, conversely, bring extra empty chairs. When a dopant atom with one less valence electron joins the silicon lattice, it essentially borrows an electron from a neighbor, leaving behind a vacancy. We call this vacancy a hole, and it acts exactly like a positively charged particle cruising through the crystal. So for our N-type materials, elements with 5 valence electrons, stuff like phosphorus, arsenic, or antimony, are integrated to provide those much-needed extra electrons. Since silicon only needs 4 electrons to complete its lattice bonds, that 5th electron from the dopant is just kind of hanging out, loosely bound. It easily becomes a free charge carrier, which drastically boosts the material's conductivity. On the flip side, to create P-type materials, we use elements with only 3 valence electrons, like boron, aluminum, and gallium. Because they show up 1 electron short of what's needed for the silicon lattice, they create those vital vacancies, those holes. As electrons jump from hole to fill them, the holes effectively travel through the material, carrying a positive charge with them. Now, to really grasp the sheer mind-boggling scale of this precision, look at this number, 1.5 times 10 to the 21st power. That's a lot of zeros. That number is the actual solubility limit of phosphorus atoms per cubic centimeter in silicon at 1100 degrees Celsius. It represents the absolute maximum amount of dopant allowed before crystal defects start to happen. If engineers push past this limit, the excess dopants actually hinder the mobility of the electrons and degrade the device's performance. It's an incredibly delicate atomic balancing act. All right, Section 4, The mighty PN junction. This is the moment we've been building up to, where these two carefully crafted materials finally meet.
What happens the exact second these materials actually touch is a beautiful balancing act. Because the N-type is packed with electrons and the P-type is packed with holes, they immediately want to mix. Electrons rush across the border and fall into the holes. But as they do, they leave behind charged ions. This creates a depleted zone, the depletion region, that eventually acts as a built-in electric barrier, perfectly balancing the flow of charges.
And this invisible barrier isn't just some theoretical concept. It generates an actual, literal, built-in potential difference across the depletion region of between 0.5 and 1.0 volts. This electric field stops any further flow of charge across the junction. It just sits there in perfect equilibrium, like a microscopic dam holding back a massive sea of electrons, just waiting for us to apply an external voltage to activate it and control the current. Which leads us perfectly into Section 5, powering modern electronic devices. Let's zoom out from the microscopic level and see how this scales up to change our entire world. So, how do N-type and P-type semiconductors actually create electronic device functionality? This is it. From that single interaction of electrons and holes at the PN junction, we get an astonishing variety of functions. Whether it's a diode allowing current to flow in only one direction, an LED giving us light, or a field effect transistor acting as the digital logic switch inside your computer's processor, every single thing scales up from that tiny microscopic exchange.
Take bipolar junction transistors, or BJTs, for example. If you take a thin layer of one material and sandwich it between two of the other, making an NPN or a PNP configuration, you create a device capable of amplifying signals and switching power with incredible efficiency. A tiny little current injected into that middle base layer can control a massive current flowing across the whole sandwich. This is literally the foundation of electronic amplification. And it doesn't stop at computers. These exact same atomic principles are powering our renewable energy future. In solar energy, advanced heterojunction structures combine different semiconductor materials, like a crystalline silicon substrate stacked with thin layers of wide bandgap materials. This engineered PN junction reduces energy loss and converts sunlight into electricity at record-breaking efficiencies exceeding 26%. As we wrap up this explainer, remember that the boundaries of doping are still being pushed every single day. Researchers are already exploring dilute magnetic semiconductors like gallium manganese arsenide, which could lead to spintronic devices that use the magnetic spin of electrons for logic circuits, or take emerging materials like perovskite for next-generation solar cells. The ability to manipulate materials at the atomic level is a constantly evolving frontier. So, knowing that tweaking a few atoms gave us the internet and solar energy, what revolutionary devices do you think are just one atomic breakthrough away?